Quadratic functions and their properties. So this is chapter 3, section 3. Take note that we do not cover sections 1 and 2 of chapter 3 in this course, so that's why we skipped over those. You didn't miss any videos. So quadratic functions. Quadratic functions are functions that can be written in the form f of x is equal to a x squared plus bx plus c, where a, b, and c are real numbers, and a is not equal to 0. Now, the reason a can't be equal to 0 is because if it is, then the x squared term disappears and you end up with f of x is equal to bx plus c, which we should all recognize is a linear equation, not a quadratic. So therefore, a can be any real number, it just can't be 0. The domain of a quadratic function is the set of all real numbers. Now, the range varies depending on where the vertex of the parabola that's formed is. So realize that, but the domain is all the set of all real numbers. So if we're going to graph a quadratic function, then we can say that h is equal to negative b over 2a and k is equal to 4ac minus b squared over 4a. Therefore, f of x is equal to a x squared plus bx plus c can also be written as a, some constant, times x minus h squared plus k, which you will recognize, or I hope you would recognize, that that's really a parabola that, x squared, every time you have x squared is a parabola, that's multiplied by a, which gives you a vertical stretch or shrink that's shifted to the right by h units, or if h is negative, to the left by h units, and shifted vertically by k positive it goes up, k negative goes down. The vertex is at hk, and the axis of symmetry is x equal to h. Now let's look at this h just a little bit here. We said h is equal to negative b over 2a. Well, if we think about quadratic functions, quadratic formulas, right? We use that. If you think of the quadratic formula, if we make the discriminant, what happens underneath the radical, equal to 0, then there is only one possible x value, right? Because you end up with negative b plus or minus 0 over 2a. So it gives us 1 point. So if that discriminant is equal to 0, there is only one possible x value that will do that, and that will be on our vertex, and it will be negative b over 2a. Now this k, that formula gives you the y value of your vertex, but personally, I don't use that a lot. I will show you an example where we use it, but in general, I just like to find the x value of the vertex, and then I just plug that into the function and get the y value that way. It works easiest for me. My personal preference, if you want to use the formula and memorize that, go ahead. But I don't. I tend to just plug it in. And also notice with the vertex being at HK, axis of symmetry, remember the axis of symmetry is that mirroring point, basically where we can fold over the parabola on top of itself. And obviously that's a vertical line that passes through the vertex. So therefore the x value of the vertex gives us the axis of symmetry, x equal to h. Well, how do we find the x-intercepts of a quadratic function? Obviously, we're going to use the quadratic formula. So if we're using the quadratic formula, then we can look at the discriminant to tell us a little bit about the function. And so if b squared minus 4ac is greater than 0, if it's positive underneath the radical, the graph of f of x has two distinct x-intercepts, because you're going to have negative b plus or minus whatever we get from that radical over 2a. So it's going to give two distinct x-intercepts. If b squared minus 4ac is equal to 0, then the graph of f of x is going to have one distinct x-intercept, because you're going to be plus or minus 0. So it's going to give you the same thing. And that x-intercept is going to be the vertex. And if b squared minus 4ac is less than 0 or negative, the graph of f of x has no x-intercepts. So it doesn't cross the x-axis. Well, let's look at a formula and look at it here. So we got f of x is equal to negative 5x squared plus 40x minus 77. And I want to find the vertex, the axis of symmetry, the y-intercept, the x-intercepts, whether it opens up or down, and associated with that, whether it has a minimum value or a maximum value, and at what point does that occur. So working through these, we know we have our formulas for the vertex, so we can find h equal to negative b over 2a. So h equal to negative 40 over 2 times negative 5, which reduces to 4. And k equal to 4ac minus b squared over 4a. So 4 times negative 5 times negative 77 minus 40 squared over 4 times negative 5, which gives us 3. So there's my example of plugging it into the formula. Although normally what I would do is I would just take the 4 and plug it in place of x in our original function and calculate k that way. And if you do that, you'll find out it still turns out to be 3. Having the vertex, we now have 4, 3 as the vertex. And using that, the axis of symmetry is going to be the vertical line x equal to the x value of the vertex, so x equal to 4. Y-intercept is where it crosses the y-axis, so that's when x is equal to 0. So if we set the x value is equal to 0, then we get negative 77. Or the quick, easy way is whenever you're finding y-intercepts, that means you're setting any x values to 0, which means it's just going to wipe out any terms that have x in them. So you're just going to be left with the constant term. So in this case, negative 77. So I didn't really even have to think about it. Y-intercept, negative 77. It was the only constant term. X-intercepts, we're going to set y equal to 0 or f of x equal to 0. We're going to use the quadratic formula. So using the quadratic formula, we get this whole nasty thing. Remember, that's negative b plus or minus the square root of b squared minus 4ac, all of that over 2a. And we come out with 2 values. And these are approximate values because we end up with radicals that are not perfect squares. Therefore, we come out with approximately 3.23 and approximately 4.77. And you can see that those are balanced about the vertex. 4, 3, right? If we've got axis of symmetry, x equal to 4, we're going down by about 0.77, 3.23, and up by about 0.77, 4.77. So those center around it, which is good. Well, does it open up or down? That can always be done by looking at the leading coefficient. The leading coefficient is negative, which would be a reflection over the x-axis, which means that it opens down. And then min or max, and at what point? If we're opening up, then we must have a minimum value. If we're opening down, we must have a maximum value. So it's a maximum value, and that value is going to be at the vertex. So we have a max at 4, 3. Another thing to look at is finding a quadratic function given its vertex and one other point. So if the vertex hk and one additional point x, f of x, on the graph of f of x equals ax squared plus bx plus c, where a is not equal to 0 because otherwise it wouldn't be a quadratic function, are known, then f of x is equal to a times x minus h squared plus k can be used to find the quadratic function. Because really any quadratic function can be written in this form where it's being, your vertex, and it's being shifted in some sort of way or a stretch or shrink. So what can we do to figure this out? Well, hk, we're already being given, that's the vertex. We're being given also one additional point, which gives us an x value and its associated f of x value. Having that, we can substitute our vertex and that one point into the function in the format we want, a x minus h squared plus k, and we can solve for a. Once we solve for a, we can substitute that and the vertex into f of x equals a x minus h squared plus k, and that gives us the formula or the equation for our quadratic function. So let's take a look at one of those. What if we have a vertex at -2, -5, and a point at -3, 2? Well, remember, we want to get into the format f of x is equal to a x minus h squared plus k. So plugging in our -2 for h and our -5 for k, we get f of x is equal to a x minus -2, the quantity squared, minus 5. So we're going to want to solve this for a, so we need to plug in the point -3, 2 also. So we plug in 2 for the f of x, -3 for x. We still have our vertex thing in there, so that's where we have 2 equal to a times -3 minus -2, quantity squared, minus 5, giving us 2 is equal to a times 1 minus 5. A times 1 is obviously a, so we can add 5 to both sides, and we get a is equal to 7. So now that we have that a, we can plug that into our generic formula with the vertex in there. So f of x is equal to 7 times x minus -2, the quantity squared, minus 5. And at this point, it's up to you whether you want to change that x minus -2 to x plus 2. Either way is fine. I wouldn't take off points either way. One is more descriptive of what the h value is. The other one is a simplified form. So both of those are perfectly valid, and I'm very happy with both of them.